We're now on to the fourth and final page of the handout on the introduction to trigonometric functions based on a right triangle. And what we'd like to do here is to show that on the unit circle, the x-coordinate is always the cosine of theta, and the y-coordinate is always equal to the sine of theta, where theta is the angle formed by the ray that we're using to locate the point on the unit circle. Well, it turns out I've got just exactly what I need here, which is my hot shot flying insect killer. And the reason I need that is because it's really a good way of making a circle. And so I'm going to put this right down here and draw a circle. Well, there we have it. And as you can see, you could hardly get a better circle than that. Ray coming up here and intersecting that circle. Now we're assuming that we're working with right, we got right angles in here, and that the radius of this circle is 1, and that we're centering it at the point 0, 0 there. Okay, now the claim is that the x-coordinate of this point, no matter what this angle theta is the cosine of theta, and the y-coordinate of that point is always the sine of theta. And at least we'd like to show this in the first quadrant here, and we'll comment on the other 3 quadrants after we got this done. Well, we already know the drill. The way you do this is you put in a line that's perpendicular to the x-axis. Draw it right in there. And then we say, all right, now the sine of theta is the opposite over the hypotenuse, but of course the hypotenuse in this case is just plain old 1. So that's the length of the opposite side divided by the hypotenuse. It's just the opposite in this special case. And what is that height? Well, that height, take a look at it. If we computed the sine of theta, it would be this distance right here, which is the y-coordinate, right? So that'd be y over 1, the y-coordinate. And what about the cosine of theta? Well, the cosine of theta would be this distance right here. That's the x-coordinate of this point. So that would be x over 1. And of course, that's just plain old x. And hey, I think we got what we want right here. The x-coordinate is the cosine of theta. That's what we have here. And the y-coordinate is the sine of theta. And that's what we have there. So that absolutely does work in the first quadrant. Now, we've said a little bit before about what do you do for sine and cosine if you're outside of the first quadrant. Say you were over at this angle right here. Well, what you do, this is our new value of theta right here, this big angle, is you look at the reference angle, which is, remember the old trick we said, well, tie a string on there that's loose on both ends, put a balloon on one end and a brick on the other. So we got our balloon here, we got our brick down here, and you're guaranteed to form a right angle with the x-axis. It's right here. This is our reference angle in here, and you just compute the trig function based on this, and then you figure out the sine later. Well, that picture would be just the same as if we had drawn it over here, right? So that height would still be the sine, and that x-coordinate would still be the cosine. It's just that you have to choose the plus or minus value depending on what coordinate you're in. And in fact, that's how we define whether the sine or cosine is positive or negative, is on these quadrants. So once again, you're going to have for the x coordinate the cosine of theta, and for the y coordinate you'll have the sine of theta. And as a matter of fact, it works all the way around the circle. And so there you have a quick outline of at least the idea of a proof that the x coordinate is cosine and the y coordinate is sine. Now, there's one last little thing we could squeeze out of here. This is just a little bit of text I'll allow you to read on your own. But that is, we could start to get an idea of what, say, the graph of the sine of theta looks like. That's the y coordinate here. You could also do it for the x. So let's just sketch a line here and just start to draw this out a little bit. So the idea is, if we had our x coordinate here, we're going to map out what the sine function looks like as we rotate around the circle. And we're going to put in these special values. And just think about what this should look like. And it turns out that all the values are going to fall between -1 and 1. Of course, that's 0 right there. And it's not too hard to figure them out. When you start right here, remember that we're thinking about the y-coordinates. Think about the y-coordinates as we move around here. Well, what's going to happen is the y-coordinates start at 0, and they start climbing up, 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 up until they crest at 1. And then the y-coordinates are going to drop down, down, down until they hit 0 again. So you start with 0, it rises up to 1 by the time you get to 90 degrees, and then it's back to 0 when you get to 180 degrees. So back down here on our graph, once you get to 90 degrees, it's got to be up to 1, and it's going to do that in a nice smooth way. You could predict that from just the physical layout there. And then back down here. And then what's going to happen as you start coming around the circle is you notice that the y-coordinates go negative, right? So they start at 0, they go negative all the way down to -1, and then they increase back up to 0. So it's the same shape. Going to bottom out at -1 here, but now it's underneath the x-axis, and you get this kind of a pattern here. Now, I am not really great at sketching, so my graph doesn't look just perfect, but that is not bad. And if you wanted to see a little better picture of it, what we could do is we could look at our calculator, and it's actually going to be more convenient if we switch modes here. I'm going to ask this to compute in radian mode, because that way I can be sure that I'm getting the right scale. We just want to see the shape, so we're not really looking at a lot of detail here. What I want is the sine of theta, or the sine of x, what the calculator is going to call it, and I would like to take the trig option on the zoom, and looks like I got some data in there, some straight points. Stat plot. Let's turn those off. And there we go. The part that we drew or sketched by hand was this piece right here, from 0 to 360 degrees. And the reason this keeps going is if you think about it, draw your ray in here, let it sweep around the circle. Well, what would happen if you swept around the circle the second time? Well, the answer is it would do exactly what it did the first time, and the same for the third time. So this graph just goes on and on forever in this kind of a wave form, and that is what the graph of the sine function looks like. The cosine looks a whole lot like it, except when you think about the x-axis, the x-coordinates are going to start to 1 and go down to 0 and then go to -1, right? So if I had used the cosine in here, it would look pretty much the same, except we'd be starting at 1 rather than 0. And there it is, starting at 1 and then down to 0, negative, back up to positive. But it repeats that over and over again forever, because those x-coordinates are going to be just repeated as you go around this circle again and again. So that's it. We really have a pretty good handle on the how to compute the trig functions for a right triangle. what to do for all of the special angles, and even some sense of what the sine and the cosine look like if you were to graph those functions.